Hi, welcome back to another Math 112 lecture. We're going to finish up Chapter 8 today with a discussion of parametric equations. Now, parametric equations are a way to describe more complex relationships than can be described as just one variable as a function of another variable. We use parametric equations when, for whatever reason, we need to look at the behavior of two different variables that are somehow related to one another, but are both also independently related to a third variable. One example of this is the height and weight of a child. Well, actually, the height and weight of a teenager. This isn't data for a child. But what I have here on this slide is a graph of weight as height increases, and we can see there's a relationship. But we can also see from the data up here that each one of these quantities is independently related to age. So if we look at that separately, so what I've got here is height. The blue dots are height. The red dots are height. The blue dots are weight. And each of these, we can see, has got an independent relationship with age. Height begins to slow down before weight does. Right? We've seen this when teenage boys between 17 and 18, they don't get much taller, but they fill out and get broader, more muscular. This is an example of a parametric relationship. So which graph is correct, the first one or the second one? Well, the answer is both of them are correct. They both show a relationship between height and weight. If, however, you want to know how each height and weight relate not only to one another, but also to age, then you want to use the second one. The correct graph really depends on the application and what information you're trying to communicate. The same thing is true when we use equations to express parametric relationships. So, for example, this is a parametric equation. This is a set of parametric equations. We've expressed both x and y as functions of t. And we're going to look at this graphically. And the way we do that is we start with a table of values. So all I did here was I created this table. I picked some values for t, and I plugged t's into the equation for x, and I got out some values for x. And I plugged these same t values into my equation for y, and I got out some y's. And then I just plotted those on a standard x-y curve. So, a couple of things to point out. This is a standard Cartesian coordinate plane. X is the horizontal axis, y is the vertical axis. Notice t does not specifically appear in the graph. The next step here is to draw a smooth curve through the dots. So, something like that. And then because it's parametric, we put on arrows to indicate movement. So we start at the lowest t. So this is t equals 0. Oops, sorry, not -0. -2. -1, 0, 1, and 2. So when you're looking at a graph, the parametric relationship might not always be evident. And it turns out, actually, that we can collapse this parametric equation into a single Cartesian equation, and we'll do that in a little bit. We can also have trigonometric relationships in our parametric equations. And I've done exactly the same thing here. I've started with a table of values. I've plugged in my t's and gotten values out for x and y, plotted those values on a standard xy Cartesian coordinate plane. And if I actually draw a curve through these, you'll recognize the shape as a circle. And in fact, we're going to let Desmos do that for us because Desmos is better. Maybe we're not. Okay, never mind. It's a circle. Trust me. So this is actually a circle. So what I have up there is the parametric expression of a circle centered at the origin with radius 3. Now, I mentioned a minute ago that we can convert from parametric to Cartesian. And this ability relies on the ability to be able to solve one parametric equation for t. So as long as we can solve one of our equations for t, in other words, as long as one of our parametric equations is invertible, then we can use that result to eliminate t from the system. And that's really what we're doing. If we have trigonometric relationships present, we want to be sure and use our identities to combine the two equations. So this is the same example we looked at earlier. Let's write this as a Cartesian equation. So here's what we're going to do. We look at our two equations. We've got x of t equals t to the third minus 1. And we've got y of t equals t minus 2. One of these is easier to solve for t than the other. Pick the easy one. So I'm going to solve the second equation and say, well, that means that t equals y plus 2. Now I'm going to take this expression and plug it into my top equation everywhere I see a t. So x now is going to equal y plus 2 to the third power minus 1. And if we were to graph that, we would get exactly this same graph. It's a cubic turned sideways, shifted to the left 1 unit, and down 2 units. Okay, here's the down 2 unit. Wait. Oh, my numbers are wrong, guys. Okay, the process I explained to you was correct, but all of my numbers are wrong. I did this, well, that one is wrong. Just that one. Okay, this one should be right here. Okay, sorry. Just one number was wrong. Okay. All right. You may be thinking, wait, those transformations don't work. Well, that's because we have not actually expressed this as a function of y, right? This is x as the dependent variable, y as the independent variable. This is backwards of how we usually do it. It's perfectly valid. You can probably stop here. My math may want you to solve this for y. Just read the answer notes, okay? You know how to solve that for y if you need to. Okay, let's try this again. This one's a little bit more complex, but again, it's not that bad. Just pick one of the two equations to solve for t. You can do either one. I'm going to use this one. Okay. So x equals the cube root of t minus 2. That means the cube root of t equals x plus 2. So t equals x plus 2 to the third power. We'll take this expression, plug it into the second equation in the place of t, so we get y equals the natural log of x plus 2 to the third power plus 1. only one little caveat here. You see this guy right here? My original equation, my original y, is only defined for t greater than 0 because you cannot take the natural log of anything less than or equal to 0. So that means that we need to limit our domain of our combined equation to x greater than -2. So this is our equation. This is our domain limitation. One more example. We're going to write this as a Cartesian coordinate. Now, first thing I'm going to do is I'm going to solve the first equation for cosine t. Isolate my cosine. And then I'm going to isolate my sine. And what I'm going to do now is I'm going to remember that the cosine squared of an angle plus the sine squared of that angle is equal to 1, which means that cosine squared t plus sine squared t will equal 1, which means then that x over 4 squared plus, whoops, this one's wrong, y over 5 squared equals 1. Or we can write that as x squared over 16 plus y squared over 25 equals 1. This equation actually describes an ellipse in space centered at the origin. And we'll talk more about the shape of that ellipse in the next section. Okay, we can go the other way too. We can go from Cartesian to parametric. This is called parameterizing an equation. It can be actually very trivial in simple situations, and I'll show you that. So we've got x equals sine y plus y. Pick the variable that is involved in the most complex way. So in this situation, we could not solve this equation for y because we've got a y inside a trigonometric function and a y outside a trigonometric function. So we're just going to say y of t equals t. Okay? So now, anywhere we see a y, we're just going to substitute t. Really, it is just that simple. Okay. Let's look at a slightly more complicated example. And this one's kind of silly. Your textbook has better examples, but we'll go through this one anyway. There's a couple of ways we could do this. We want to parameterize a line passing through these 2 points. The easiest way to do this, so I'm going to make a table of values, t, and I'm going to call this an x and a y. And I've got a t1, and x is 1, and y is 5. And I've got a t2, and we could pick any value of t's here that we want. It really doesn't matter. And x is 2, and y is 1. So we only have 2 points. So we're going to have to assume that both x of t and y of t are linear. Okay? So we're also going to make an assumption that we can set our t values. I'm going to say this is t equals 0 and this is t equals 1. I'm only going to do this. Actually, I'm not going to do that. I'm going to leave those as t1 and t2. But we are going to say that t2 minus t1 equals 1. So there's only one step in our parametric variable between these 2 points. So x of t is going to equal some slope times t plus some y-intercept. we can actually pick this y-intercept. We've got a lot of freedom when we're doing this. So I'm going to say that if t is 0, and we're just going to leave that alone for a minute. Okay, so we can find the slope. M sub x is 2 minus 1 over t2 minus t1, which is 1, so that's just 1. So x of t is going to equal t. And we're going to pick this, and we're going to say that this guy is 0. So we're just going to make x of t equal t. No big deal. Now let's look at y. And we could do this a couple of ways. The easiest way is to do what we did a minute ago, but let's try it this way. So actually, yeah. So now we're going to say y of x equals the slope between these 2 points. So it's 5 minus 1 over 2 minus 1 times x minus 2 plus 1. I'm using the slope or the point slope form of the equation of a line. So y of x equals 4 over 2 is 2. X minus 4 plus 1 is minus 3. We've already said that x of t equals t. So y of t is 2t minus 3. Sorry. Okay, your textbook's got some additional good examples, so do read this section in the text. But that is it for this recording. I hope if you have any questions, you'll reach out to me either through the forums or directly through email. And I will see you all again soon. In the meantime, have a great day, week, whatever it is, and always do good math.